Crossed fields, discovery of the electron. Both an electric field E and magnetic field B can produce a force on a charged particle. When the two fields are perpendicular to each other, they are said to be crossed field. Here we shall examine what happens to charged particles, namely electrons, as they move through crossed fields. We use as our example the experimental that led to the discovery of the direction electron in 1897 by J.J. Thomson at Cambridge University. Figure 28.7 shows a modern simplified version of Thomson experiment apparatus, a cathode ray tube, which is like the picture tube in an old type television set. Charged particles, which we now know as electrons, are emitted by a hot filament at the rear of the evacuated tube and are accelerated by an applied potential difference V. After they pass through a slit in screen C, they form a narrow beam. They then pass through a region of crossed E and B fields, headed toward a fluorescent screen S, where they produce a spot of light on a television screen. The spot is part of the picture. The forces on the charged particles in the crossed fields regions can deflect them from the center of the screen. By controlling the magnitudes and direction of the fields, Thomson could thus control where the spot of light appeared on the screen. Recall that the force on a negatively charged particle due to an electric field is directed opposite the field. Thus, for the arrangement of figure 28.7, the electrons are forced up the page by electric field E and down the page by magnetic field B. That is, the forces are in opposition. Thomson produced procedure was equivalent to the following series of steps. Set E is equal to 0 and B is equal to 0, and note the position of the spot on screen S due to the undeflected beam. Turn on E and measure the resulting beam deflection. Maintaining E. Now turn on B and adjust its value until the beam returns to the undeflected position. With the forces in opposition, they can be made to cancel. We discussed the deflection of a charged particle moving through an electric field E between two plates in the sample problem in the preceding section. We found that the deflection of the particle at the far end of the plate is y is equal to q e l ka square over 2mv ka square, where v is the particle speed, m its mass, and q its charge, and l is the length of the plates. We can apply this same equation to the beam of electrons in figure 28.7. If need be, we can calculate the deflection by measuring the deflection of the beam on screen S and then working back to calculate the deflection Y at the end of the plate. Because the direction of the deflection is set by a sign of the particle's charge, Thomson was able to show that the particles that were lighting up his screen were negatively charged when the two fields in figure 28.7 are adjusted so that the two deflecting forces cancel. We have form in which all equations on the right can be measured. Thus, the crossed field allows us to measure the ratio m over q of the particles moving through Thomson apparatus. Thomson claimed that these particles are found in all matter. He also claimed that 1000 his m over q mod square measurement, applied with the boldness of his two claims, is considered to be the discovery of the electron.